大范围的推广还是更本质。对压缩早期很多那个漂亮工作，在这都是昨天我跟吴老师全覆盖。刚做了一段时间。
Okay, so good morning, everyone. Welcome to the morning session of this room. And there will be two plenary talks. And the first speaker is Professor Zhengwei Liu from Tsinghua University and also BIMSTEC. The title of his talk is Outer for TQFT and Topological Orders in All Dimensions. Let's enjoy.
Thank you for the introduction, and it's a great honor to give a talk at the ICBS. And today I will talk about a topic about topological quantum field theory and topological orders. Somehow this has been well studied in lower dimensional case, and but in this talk, well, we will talk about lower dimensional case, but we will also show how this turns out to be very natural in higher dimensions as well, and what's the major difference. And also we will give examples in higher dimensions to illustrate our ideas. And this is joint work with our colleagues at BIMSA, Shuangming, Yilong Wang, and Jinsong Wu. So first, Wang Jun discovered the quantum invariance of knots by studying the index of subfactors, which is a topic in our operator algebras. At the beginning, it seems not relevant to like topology at all, but it turned out that by studying the so-called bimodules of in operator algebra, or somehow the representations of subfactor, we can get very interesting topological structure, like template algebra and graded representation, and eventually it leads to the Jones polynomial, which is the first quantum invariance of knots and links. And it satisfies this kind of quadratic relations, and which satisfy the mathematical moves. And the value of a closed circle is the square root of the Jones index. And then actually he observed that the braid appeared in his algebra. It's actually related to the so-called Heck algebra, which can be further related to the representation theory of quantum groups, UKSL2. And at that point, it was not considered a quantum group. It was studied in the integrable system by Jimbo, and they found the solutions of the Yang-Baxter equation. And later, there's a machine to produce such solutions using quantum groups. And also, by studying the representations of quantum groups of the Greenfield Jimbo type, and then one can obtain those kind of braids in a very natural way, and braid group representations, and also link invariance, which generalize the Jones polynomial. And the theory of Jones polynomial becomes the theory of SU2. And then it turns out to be even more interesting that this kind of invariant has a very nice topological meaning in the physics literature in quantum field theory. And somehow they turned out to be interesting topological invariants of quantum field theory. And that can be formulated as a topological quantum field theory. Okay. Wait. Where's the slides? Okay, one slide is missing. Well, so in the topological quantum field theory, well, we can study this topological quantum field theory by showing that one can actually construct a quantum field theory and recover the Jones polynomial through Path integral using Chen-Simon theory, and which is a form that is topologically invariant. And then, well, there is a problem that the Path integral is not mathematically well defined, but from that construction, we can axiomatize all the structures out of this. And then from like the representation theory of quantum groups, we can make it more rigorous. And using more generally, we can start with say the representation of quantum group as a braided tensor category, and construct the 2+1 TQFT using the surgery theory of licorice Wallace. And this kind of environment is called the weighted Rushdie-Taken environment. And also, if we study in a more general situation the representation of Hopf algebra, we can also get the fusion category without the braiding. And that's also the case in operator algebra by studying by modules. And then we can get the state sum formula of 12 Vero and Barrett Westbury. And this kind of environment turns out to be also very natural, and we can say start with representations of groups to get such kind of environments. It's crucial that the group has to be finite order, or the number of irreducible representation of a quantum group has to be finitely many, such that the state sum is a finite sum, so it's mathematically well defined. And at that time, Witten, Greenfield, and Jones, they all win the Fields Medal in 1990s in Tokyo. And for the higher dimensional case, people are trying to understand what's going on in a higher dimensional topological quantum field theory. And then, well, first, somehow we have an invariant of n manifold, and then we can cut the boundary. So that we have a closed n-1 manifold on boundary. And then one can consider all kinds of manifolds with such boundary spans a vector space. And the cobordism just acts on this vector space. And this is proposed as a TQFT, topological quantum field theory. This becomes a symmetric monoidal functor from the category of cobordism to the category of vector spaces. And then people ask further, okay, we can cut the boundary, we get codimensional 1 space, and we cut it further and get codimensional 2 space and higher codimensions called corners. And then there should be further analog on the other side, on the algebraic side, or in terms of kind of algebraic topology. So that's from scalar to vector space and then to higher categories. And this has been proposed as a cobordism hypothesis. And in principle, to study the n-dimensional TQFT, well, that's essentially studied a symmetric monoidal n category with a fully dualizable object. And this is proposed by Bass and Dolan in 1995. And it's proved by Hopkins and Lurie in dimension 2 and by Lurie in general case for all dimensions in 2009. So one can study those kind of higher codimensional corners in the TQFT through the n category. This is kind of algebraic topology approach to the topological quantum field theory. And there's another interesting direction. It seems not directly relevant at the beginning, but it turns out to be quite close theory, more or less parallel. That's called topological orders. Now, there have been very interesting topological phenomena from condensed matter physics, like topological insulator and quantum Hall effects and many other things. And people are studying the ground states of Hamiltonian and found that the ground state has some very interesting topological invariants behind that, some global phenomena, even though the Hamiltonian is defined locally, but eventually we can see some global phenomena. And this doesn't happen in the one-dimensional case, but it does happen in the two-dimensional case. And a very remarkable model is given by Kitaev. It's called torus code. So we can build a lattice on a torus and study the local Hamiltonian, and such that the ground state becomes four-dimensional. So why four-dimensional? So we consider that as two logical qubits, so 2 times 2. And they correspond, number 2 corresponds to the homology group of the torus, the longitude and the altitude. And in general, Leibel and Wien studied more general symmetry that's beyond this kind of group-like symmetry, and that's given by the categorical symmetry. And then the ground state actually captures the very interesting categorical symmetry, and that produces highly entangled states, and with interesting entanglement. And those kind of structure has been considered to use to build quantum error correction codes. And so far, actually, it's a very popular scheme to build such quantum error correction codes, and it's topologically protected codes that's to implement fault-tolerant quantum computing. So, like Xiaogang, when he proposed those ideas that we should study those kind of states, go beyond group symmetry, and to study those kind of more categorical symmetry. Somehow the group symmetry are more or less invertible given by the group action, but the categorical symmetry really goes beyond those group elements. And actually, from the view of algebras, somehow, well, the group symmetry is a special case of the categorical symmetry. That means we can multiply two group elements, G and H, we get another group element. But on the categorical level, like for the representations, we can take tensor product of two representations, then it decompose as direct sums. So it's not just a single term, it has more terms. So it has more linear structures, which coincides with those quantum, like the linear structures in quantum field theory. And then, like Wen Kong, Xiaogang Wen, Liang Kong, and Zhenghua, and many others, they have investigated the higher dimensional topological orders through the n categories, and in particular, the very general theory. And a monoidal n category is supposed to be a good source to construct n-dimensional topological orders. So that's somehow a highly entangled states on the lattice. There's no way to change that to like product state, the trivial state, by some local transformations. And because the topological invariant, it's a strong abstraction to make it to just a simple tensor product. And there are examples like that, like the group cohomologies. We can start with the group cohomology theory and to construct an n category that's called the invertible n category, since all the objects are group-like and they are all one-dimensional. And then also construct the TQFT, n plus 1 TQFT, and that's the Dycroft-Witten TQFT. However, if we want to do something non-group-like, it's really difficult. It's lack of source to construct such non-group-like n categories. Well, there are obvious reasons. Like for the groups, it's essentially Hopf algebra. We can go beyond. We can get Lie groups, get deformation to get quantum group, and we get many resources to get interesting two categories. But to get a higher category, we need a higher analog of the quantum groups. But it's lack of literature of such topics. So how to study those higher dimensional topics? What's the right generalization of the groups? It's still not that clear. And actually, we need a lot of additional structures to really get the topological orders. In particular, to get a reasonable physical space, we need the unitary condition. The vertical space should be a Hilbert space. And it's very difficult to impose this kind of positivity condition on the higher dimensional case. So there are many, many challenges to construct interesting examples. Even though we have fruitful theory and we have a lot of expectations and we have a lot of evidence, it seems that the theory in lower dimensional case, like 2 plus 1 or even 3 plus 1, should be naturally generalized to higher dimensional case. But constructing examples is really difficult. Now, what should we expect from the theory of n-dimensional topological order, and how it should be related to n plus 1 topological quantum field theory? So we learned some lessons from the 2 plus 1 theory, like the 2D lattice models of toric code, or Liu model. So first, we expect to have a good Hamiltonian, sometimes gapped, sometimes gapless, and it's defined on lattice, and on, say, local part, local open disk. And somehow we can refine the lattice and take the large-scale limit or continuum limit. So you can change the shape of the lattice. But locally, the Hamiltonian looks the same for a local piece. And then we want to glue the local piece, the local DN piece, to a global n manifold. And then we get the lattice on the manifold, and we get some global structure. In particular, we should have invariance of such n manifold. For example, we can look at the ground states of this Hamiltonian, and we can count the dimension of the ground states on the manifold. And to ensure this is something topological, somehow we want to require the dimension of the ground state or the degeneracy is independent of the shape of the lattice. Like for example, in the toric code case, when we look at the torus, it doesn't matter how we take the size of the lattice. The number of the ground states is always 4-dimensional or 2 logical qubits. And the two really comes from the topological behavior of the torus, not the lattice. So that's kind of a key point to relate the theory of this ground states of Hamiltonian and the theory in TKFT. So in particular, we expect that the ground state, the space of ground states, should be really the space in a topological quantum field theory. So we want to construct the n+1 topological quantum field theory such that on the boundary n manifold, the space of this n manifold is identical to the space of the ground states of the lattice model. And of course, there is some ambiguity since when we change the lattice, the Hilbert space is changing and the ground state look different. So we need some natural bijections among different lattices. So we need to identify the ground states in the lattice model and this kind of more abstract states in the TKF or vectors in the TKFT. And furthermore, well, such ground states are usually highly entangled based on the symmetry, non-trivial symmetry. And we expect those topological structure gives non-trivial constraints on the states, and this will produce non-trivial topological orders. And we expect that the TKFT will capture the symmetry of topological orders, or the states, just the topological symmetry. So it's actually even more than the categorical symmetry if we consider TKFT. So categorical symmetry tells the local symmetry of the states. That's kind of the localized symmetry at a point or in a small neighborhood. That's a categorical symmetry. But the TKFT not only tells the local symmetry, but also the global symmetry. So two different kinds of symmetry. So in this sense, we consider TKFT to be somehow more general. In particular, from the construction, we start with something like if we start with the n category, that means we start with a system with local symmetry, and eventually we produce a system with non-trivial global symmetries. And also, since it's a TKFT, then for a closed n+1 manifold, we should have a partition function, and that is topological invariant. And we expect this invariant to be non-trivial. So why do we mention that? Since there are actually constructions like from if we start with a 2D theory and then get a 2+1 TKFT. And actually we can go further. We can get 2+1 + 1 TKFT. And actually we can go further and further. Later we will see a construction that will work in this way. But when we go to 2 steps, the topological invariant becomes trivial. It's just constant 1. So in that way we do have a TKFT, but the topological invariant is no longer that interesting. So somehow the most interesting part of theory is going from the n-dimensional theory to the n+1 dimensional theory. We can go further, but we don't have that much information. This is kind of the mysterious for this favor in the lower dimensional topology. Like usually in algebraic topology, we study the topology in all dimensions together. But this is kind of a theory. It's so sensitive at dimension n and n+1 rather than all the dimensions. Even though we can construct models for all dimensions, but there is really a distinguished dimension that's most interesting. Now let's get into the main result. So what do we do? So we can construct such n-dimensional topological orders and an n+1 dimensional unitary TKFT. We call it the orthofold TKFT because the TKFT has 2 different colors in the top dimension, A and B. Later we will explain what's the meaning of the 2 colors. And the color appear alternatively. And somehow the original 2D theory will live on the domain wall between the AB colored top dimensional bulk. So in that way, we extend the n-dimensional theory as the domain wall theory between A and B. And actually the A theory will be the vacuum theory. So essentially it's the boundary theory on the bulk B color part. So this will be a kind of bulk boundary duality in all dimensions. Yeah, orthofold we will mention. So fold is just like a manifold. And orthofold really means, okay, for the manifold we have two different colors in the region. And they are colored alternatively. And then between two colors, we have the codimension 1 manifold. Like in the 2D surface, we can have lines or circles on surface, and it has alternating color for the two cells. And for the 3-dimensional case, we can have kind of two surfaces, the 2-dimensional surfaces, and the kinetic component of the 3-cell or 3-dimensional regions are colored in A and B. So if you ignore the A color part, then it's even easier to state that. Just you have a n-dimensional or n+1 dimensional manifold with boundary. And the original theory lives on the n-dimensional boundary. And the n+1 manifold is colored by B, the bulk color. So this essentially is a theory with two kinds of boundary. Not like the usual TQFT, we have kind of time boundary that we can take composition. This theory also has a space boundary. Right? We call that TQFT with space-time boundary. And then to construct such a TQFT, so what's the input data? Now we need a linear functional on those lattices. So the lattices are somehow Hilbert spaces given by a tensor product of those local spins. Now we want to define a linear function on that when the lattice is defined on a sphere, like on n-dimensional sphere. And we require 3 properties. First is isotopy invariant. That means we can take isotopy, like piecewise linear isotopy of the lattice on the sphere, and we require that this function is invariant under such isotopy. So essentially we only care about the shape of the lattice rather than the precise position. This captures the topological behavior. And the second crucial condition, well, the first condition is really easy to implement. The second one is really crucial. That's the reflecting positivity. So we require certain positive condition for this function. So what's the meaning of that? So if we want to define a function of a sphere, then somehow we can cut the sphere in the middle and get 2 disks. And then this function essentially defines the inner product between the disks. And we require this inner product to be a positive inner product. So it makes the vectors on the disk into a Hilbert space rather than just a vector space. And that's its reflecting positivity. So that's a crucial condition to get a unitary theory. But that's actually the common condition in quantum field theory. And third one is completely finiteness. For example, when we fix the boundary of the disk, we can take arbitrary shape of the disk. The vector space is certainly blow up to infinite dimensional if we take all possibilities. But since we have this inner product, this will have a very big kernel. And then after we take caution of the kernel, we require this vector space to be finite dimensional. And well, this is really similar to the reflecting positivity condition in quantum field theory. That we can take reflecting positivity, we have a big kernel, and we turn an n-dimensional statistic theory model to like one direction becomes the time direction under the weak rotation. And then we have a very big kernel for that. And here we need this complete finiteness condition because later we want to define TQFT as a steady sum. And this will ensure the sum is a finite sum, so that it's mathematically well defined. So somehow, from physics point of view, the last condition may not be so necessary. But to really ensure this is a well-defined formula, we really need that. But from somehow the real crucial condition here is the second condition. But we do need to check the third condition. Now, well, we will construct a concrete example to explain the 3 properties more explicitly, but not really presenting its formal mathematical definition. And it's crucial that in this approach, we do not need a unitary n category as an input, since it's still difficult to construct such an n category. So we don't want to take some difficulty input to get something interesting. We want something more practical that we can construct. And another interesting part is, even though the theory of topological order is deeply related to the Hamiltonian, and usually we start with that, but here we just start with this linear functionals. And we will show there will be a natural Hamiltonian to implement this linear functional as its ground state. And actually, this ground state is very special. It's the vacuum state in the topological quantum field theory. And how do we expect to have so many interesting algebraic relations just from a single function, a single linear function z? And the point is just that since the kernel of z is really huge, and everything lives in the kernel, we will consider that as an algebraic relation. And that means we have a huge amount of algebraic relations. And actually, all the categorical symmetry will just naturally emerge from those algebraic relations. And also, we will see those kind of Hamiltonian and many other data in a very natural way just from the kernel. So even though essentially we only require this single reflecting positivity condition, but this is a strong condition, and we learned from quantum field theory that this condition somehow should be enough. And now we give a concrete example. How do we get such kind of lattice model with a very good linear functional z that has reflecting positivity? And here, this lattice is a lattice on the 3 sphere. Now we are constructing a 3 plus 1, the example of 3 plus 1 TQFT. So we look at lattice on 3 sphere, and we are requiring some kind of topological invariance. So the function should be defined up to topological isotopy. So what's the data on the lattice? We just take surfaces in the 3 sphere. So how do you think about this as a lattice? You can just give a triangulation of the 3 sphere in any way you want. And you look each local piece of the simplex, and you look the intersection of the simplex with the surfaces. If you look at the shape, okay, that's just the data for your lattice, whatever it is. And then you combine all of them together, eventually you have a bunch of surfaces in the 3 sphere. And then we are going to define a function for this data. Then what's the function? Then we are going to take the advantage of topology. So we want to define the function using some topological invariant of surfaces, and that will be the genus or the Euler number. Okay. So then for each component, for each surface Si, we just take a value. It just contributes to value 2 to the 1 minus the Euler number over 4. And we take the product of that. And then we claim that, okay, first it's clear this function is isotopy invariant because the Euler number it is. And it's non-trivial to see this is reflecting positive. That means you can take like surfaces with boundary, not in S3 but in the D3, and glue that with the mirror image, even with linear sum, and then this function will be a positive scalar, or positive or 0. And another thing is that this will be completely finite. We will explain in the following pages what's the meaning of the completely finite is. Then just by looking at this single function, nothing else, just this single function, we can read out a bunch of very rich data, like the 3 category, 3 plus 1 TQFT, Hamiltonian, and many other further data. And indeed,
it's just a number. It's just a number which is an invariant of a collection of full surface of the isotope.
Yes. It's just number. This number is actually very powerful. For example, when Jones construct the Jones polynomial, actually only one number contributes to the algebra. He just started a 1-dimensional lowercase. He looked at the surface, not surface, like circles on S2 on the sphere. And each circle contributes to a value delta. And that's all about it.
So do you have a sort of scale module?
Yes. That's a good point. At this point, we don't have to ensure oriented surfaces. Yeah. since we only consider Euler number, so even though we have unrotated ones, eventually the series are equivalent in this case. But actually, there are other examples that will detect the difference between oriented ones and unoriented ones, and that will lead to other interesting examples. So actually, for Jones polynomial, the model is really just the circles on the two sphere, and each circle contributes to a value of delta, and delta is Q plus Q inverse that corresponds to the UQSL2.
Yeah. Well, but when we study knots, then just isomorphic classes of curves on the plane are not interesting. So then we have some over-under structure. Do you have anything like surfaces in four space, which you would use to surfaces in free space?
Yes. Yes, that's the point. So we start with this data that looks simple, but the important part is this data has reflecting positivity. That's the most important part. And then the general theory, what we call autofold T cap T, will tell us how to get all other important data, like the T cap T, the lattice model, the Hamiltonian, all kind of expected data just from the single data. So we will run that machine. So this is kind of the theory has two parts. We have this point in the middle, and that's this linear functional with reflecting positivity. And we have the general theory to produce all those rich data like higher category and T cap T. And this just always work. And another piece is, how do we get this function? How do we get such a function with reflecting positivity? And that's a theory that how we construct the examples. So this really has two different pieces. And somehow this is a good middle point. And we have kind of general theory tell us how to construct good examples and how to use the example to build richer some fruitful results. So comparing to the higher categorical approach, that means this middle point is no longer n category, since it's really very difficult to construct an n category with such kind of unitary condition, but much easier to construct just a function, a linear function with reflecting positivity. It's much easier to check this condition. And we call this the Ising type 3 plus 1 unitary T cap T because this 3 plus 1, this will lead to a 3 plus 1 T cap T, and on the boundary, it really encodes the lattice model, which is the three-dimensional Ising model. So that's kind of a really quite new mathematical structure behind the 3D Ising model, but in the one-dimensional higher space. Now I'll explain what's the meaning of finiteness. So the point is that we have those surfaces, and then we want to look at local data. When we cut the surfaces in S3 with the simplex, we want to read what do we have, like the intersection of the simplex with those data. Like on one cell, we can have the one cell intersect with surfaces, so we see several points. And we want to see the intersection of 2 cells, intersection of 3 cells, and 4 cells, and so on. And somehow we want to show the essential intersection has only finite many of types. So in what sense, like if we look at a line, we can intersect with the face 1 time, or even 0 times, and we call that the trivial. Or 1 time, we call that tau. Or 2 times. And for 2 times, then we have 2 parallel faces in the neighborhood. And then we will have this interesting relation. If we consider this as an algebra, we can multiply along this 2-dimensional. We can have multiplication of 2 disks. Actually, we can rotate them. So this is a commutative algebra. And then for the 2-dimensional case, we will have 2 vectors in the space. We may have 2 disks that are disjoint, or they are connected by a Ternal. And then this algebra is 2-dimensional, so we get 2 projections. This is identity, and the Ternal is another projection. And their difference, we call it the projection G. That's the red line, labeled by the red line. So what's the point of this Ternal? If you look at a face with Ternal, then you can look through the Ternal. You don't see anything there. So somehow that means this projection is equivalent to the trivial projection. That means it doesn't intersect with the one simplex in the middle. So that means that this tau tensor tau, the two faces, will be decomposed into two sub-projections. And one is equivalent to the trivial, and the other one is a new projection G. So we have tau squared equals 1 plus G. And this is really the Ising type fusion rule. And if we go further, we can compute. We can take G and then tensor tau again. And we can show that this is actually equivalent to tau. And if we take G tensor G, this will be equivalent to 1. And that means when we take the one simplex, we can have like many parallel folds of the faces. But modulo those relations, essentially we can only see two, at most two faces.
Excuse me, assuming you have just a broken surface diagram of the image, and is there any chance to construct a spin theory? Because it's very much non-local. You can have double lines, and so is there any chance?
Yes, there actually has very nice spin theory. So for example, if we have a face with a handle, we can remove the handle by multiplying a scalar according to the change of the Euler number.
Yeah, but you can have a double line, which is long enough, which intersects triple points that have many other double lines.
Yeah.
Yes.
Yes. So we have the full skin theory that allows us to reduce the kind of surfaces to a scalar, rather than just defining the function at the very beginning. That is the case. Oh. Yeah. So this is actually the dual picture to the higher category. So for the zero morphism, it's really the three-dimensional, the three manifold in the background, the D3, and the face is the kind of the domain wall between the two. So a single face will be one morphism. Yeah, between the two 3D color, 3D cells. So single face, we call that tau, will be a one morphism. And then when we take tau squared, we just take two faces.
So when you say that it's one zero morphism, it corresponds to any of the three cells?
Yes, any of the three cells, yes. So it's really the Poincare duals. So for the one morphism, we have those tau, and if we take this twice, we can decompose that. And if we take this three times, we can show it's always equivalent to just single tau. So that will reduce the multiple of the faces to just at most two faces. And that's kind of finiteness condition. So up to this kind of equivalence, we will get only finitely many one simplex. And then after we have the one simplex, then if we look at the intersection with the triangle, that should be like two morphisms. Okay. For the edge is one morphism, and then we make them into a triangle. That's a two morphism. And then for two morphism, we will have those one morphisms on the boundary edge. So there are three possible labels: the trivial, the single point tau, and the 2 point G. And then we just draw all possible connections of those points. And that gives us the possible labels of the two morphisms. And certainly once we fix the boundary condition, there are only finitely many possibilities to connect the boundary points. So that gives the finiteness of the two morphism. And only one thing we need to be careful. There may be additional data that's not connected to a boundary point. So that's localized, like this second graph. And this black dot is actually the circle. So we can have a like kernel intersecting with this the two simplex, and the intersection is a circle on this face of the triangle. So in principle, we can have multiple circles, even infinite, as many as possible. But we can deduce a skin relation such that when a circle meets a line, we can contract them together or fuse them together to a single line. And that will reduce the number of circles to just one. So that gives a finiteness condition for those two two morphisms. And here we write down all possibilities. First, we fix boundary condition, and we write down all possibles. And actually, the last two has no compatible condition. Here means it's tau 1, 1, and tau has just correspond to a single point. But when we connect them by like the surfaces, we will have the parity check. So this has no compatible condition. So these two won't give us reasonable two morphism. And this is actually more interesting. Here is GG1, and this is GGG. And this actually will give us a reasonable graph, but eventually this won't show up. It's kind of the fusion that G times G doesn't have a copy of G. So what happened here? For this graph, we can show it lives in the kernel of this function Z, linear function of Z. And that means any graph contains this local piece will have the value 0. So that lives in the kernel. So modulo the kernel, this will be 0. So this doesn't show up. And this actually also happened for the theory of UKSL2. When we take Q to be root of unity, we will have the last projection, the Jones-Wanzel idempotent that has trace 0. And this is a similar phenomenon. So we take interesting caution by that. And then after we have the label of the 2 simplex, we can make up the 3 simplex by fix the boundary faces. And there are like many possibilities. And then after we have the boundary for the 3 simplex with compatible boundary condition, and then we can fill the bulk and get the 4 morphisms. And the 4 morphism will be filled by those surfaces we start with, and those are vectors. And just given the previous boundary condition, we can write down those vectors. Like for example, this vector, we see this is kernel in the middle, and that means we see a single black dot on this face and another black dot on that face. And this, for this example, this is just a face intersected with 4 edges. So we will have tau, 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 tau for the 4 edges, and trivial for the other 2 edges. So we just draw all possible surfaces which bounds this with such boundary condition, and they are also finitely many. That means the vector space with the boundary condition is finite dimensional. So then we have all the finiteness for all the simplexes, and that's what we mean by the completely finiteness condition. So this can be checked for those concrete examples. And essentially we are describing the kind of the 3 category, just using 0, 1, 2, 3, 4 morphisms. And the last one will be vectors. And there are actually more. And then once we have the 4 morphisms, then we can count the higher analog of the secondary symbol. So that will be given by the value of the delta 5. And here we generalize the 6J symbol to the 25J symbols. So there are really 25 labels. Okay. And the top line will be the ID of the kind of 25J. Okay. And we have those possible labels. And then we can compute their value. And how to compute the value? We just glue all the simplexes of those delta 4, those vectors, into a delta 5. And then we get a closed S3 with some surfaces inside. And we know the function in priority at the beginning, and we compute that function, and that's the F symbol. And what should we expect for those numbers? They should satisfy the 1-dimensional higher analog of the Pantegan equation, and that corresponding to the data in delta 6. And that's the higher puncher move. And in general, we should have 3 to 3, 4 to 2, and 5 to 1, 3 kinds of puncher moves. But the 3 to 3 is the most complicated one, and that actually we can derive the others from this one. So those 25J symbols, they do satisfy the puncher moves, the higher analog of Pantegan equation. So you can imagine if you want to solve such kind of equation directly, it will be extremely difficult. But from this kind of reflecting positive linear functional, the theory tells us all those data has to satisfy those equations. And actually we checked some of the equations by computer just to ensure we have the right data. And eventually, okay, we get the right data. It's actually a bit tricky to check them because it's very easy to make a mistake, miscomputation by human. And also, when we do the computer code, it's also easy to make a mistake for the code. So somehow we need to fix them on both sides. And eventually we see, okay, many equations, just many zeros at the end. And then we know, okay, the theory works and the data works and also the computer code works. So in this case, we get this interesting data that we can use to construct a 3+1 TQFT. In particular, actually, we get a 3 unitary category. Now, how do we construct the TQFT just from such data? Well, if you are familiar with the construction from the TQFT, from the 3n category to the n+1 TQFT, this will work. But actually, when we say autofollow TQFT, we have additional data rather than the previous like 12 virial type TQFT we studied, since we have this additional AB color, such that the original n-dimensional sphere lives on the boundary. Now we will explain how to construct that, and to better illustrate the picture, we will just explain the theory for 2+1 rather than 3+1. Since for 3+1 case, the picture will be 4-dimensional, but it's difficult to show that on the slides. So we will really do the 2+1 case, but we will see this construction really works in all dimensions. And the input data is just this linear function node, which is reflecting positive. And for 2+1 case, we start with a 2-dimensional lattice model. So one can consider the data as like a light-wave model or spherical category. So now, what's the autofold? So from the 2D theory, we have we already have a 2D theory like a function, linear function of z for those configurations on sphere, or lattice model on sphere. And how do we extend that to a 3-dimensional theory? So 2D theory will be living on this what we call separating surface S, 2-dimensional manifold, and it's inside the 3 manifold. And the 3 manifold has an AB color. It's aside the surfaces. So conversely, we can say, okay, the original theory lives on the domain wall between A and B color. And so far, the 2 colors seems very abstract. So what they are, where do we get them? So how do we start with just a function on the sphere to get a 3D theory? We need to introduce a bunch of scaling relations. And the idea is following. If we have a sphere with B color inside, the bulk color is always the white color. The black is the background. And if we have a sphere, there may be additional data on the sphere. Then we just evaluate that using the function z. So the zeta is evaluated by z. And there's an additional scalar zeta. And that's a free parameter that corresponds to the value of the empty sphere with no decoration. So that's the first relation. And the second relation. So, by the way, how do we read this for all dimensions? This will be a disk, a 3-dimensional disk, multiply a single point, just a single disk. And we remove that. Okay, this is the relation. And next relation, okay, this is D3 cross D0. The next one will be D2 cross D1. So that's a 2-dimensional disk cross the interval. And we have data on the interval. And for the second coordinate, it's a small neighborhood. So we can consider this as a small neighborhood of a disk. So it will be the identity map. And then we change that to the shape of D3 cross I0, like 2 balls. And the relation will be the resolution of identity. Well, but at this point, we don't want to read this in the algebraic way. Since we only have a linear functional, we want to reinterpret this relation using linear functional. So how do we get this relation? We do the following. We kept the hemisphere such that the right side will be 2 spheres. Okay, we take a cap and cup on the right side. We get 2 spheres. And on the left side, we have 1 sphere. So we want to ensure this is equality for any possible dual structure. So this is essentially using a double dual. For this one, we can take inner product with this kind of dual picture. And on the left side, we will get the value of a sphere. So that means we use a double dual to define this relation. And we only need the inner product to introduce this relation. So that's the magic of this non-degenerate inner product from this function z. And then similarly, we can go further. We take d1 cross d2, and we change that to d2 cross s1. Okay. And again, we take the value of this picture with this dual picture, and then we will have a kind of a solid torus. But where do we have the value of solid torus? Previously, we only have the value of a sphere. Okay, we go to previous step. Now we can take the inner product of this one with this mirror image, and that will be a torus. And since this is defined by the right side, now it's well-defined value. And then using that solid torus, we can define the inner product of this one with this mirror image. And then the inner product of left and the right is again a sphere. And then we use the double dual condition to induce this relation. And then we go further. We take inner product of this one with itself, we will get the value of 2 spheres. And we consider that as the inner product between a sphere and the mirror. A sphere and the mirror. And then the inner product of this diagram with that will be just a single sphere. So again, we use the double dual to induce this relation. And this method really works in all dimensions. We just use the inner product, we induce the relation using the double dual structure. And to ensure the double dual works, that's the part we need finite dimensional condition. Otherwise, the double dual of the vector space for infinite dimensional case is no longer itself. But somehow you can imagine this theory can be generalized in a big deal. If we have something not necessarily a vector space, if we have something with double dual, then this will work. And then using this machine, we can get all those relations. And then that's how do we derive the relation using double dual. Now let's say, what's the meaning of those relations? This means given a B-colored manifold of shape D3, we can remove that. And if we consider D1 as a neighborhood, that means given a B-colored neighborhood of a disk, we can remove that. So we can remove D3, we can remove D2, and we can remove D1 and remove D0. So now if for the 3 manifold we have a triangulation, then we can remove the 0, 1, 2, 3 cells just according to the triangulation using the moves. And that will give us 3-state sum formula. And that should be the 12 zero TQFT, or 2 plus 1 theory, and it is. And in our theory, the 12 zero will naturally come up. And for the B color theory, when we remove all the B color to A color, this actually we get a quotient. It's the value of B color theory over the value of A color theory. And that's 12 zero. And then actually you can imagine, okay, what's going on for the A color? We didn't use that yet. And the A color seems to be very arbitrary. Right? We didn't take any special value for the A color. But then we fix the A color value. For any 3 manifold, we fix value to be 1. So why do we take that? Because that really tells us the surgery theory. When we fix value to be 1, that means we can change the A color manifold in any way we want. It doesn't change this partition function. And that's exactly the surgery theory. We can change the A color shape. So once we have surgery theory, actually, then we can get back to the Reshtikin 12 TQFT. And in particular, we can get the Dune field center as the data. And how do we read the Dune field center from this? We just read a point-like particle in the 3D theory. And here, the point really blow up to a closed string with A color inside, B color outside. And those, when we move those points in the 3D space, that forms a Brady tensor category. And that is the Dune field center. And on this circle, on the like the time worksheet of the circle, it's a tube. And previously, people construct the Dune field center using this so-called Ockham tube algebra. So this just naturally come up. And then if we implement the surgery theory, we can get the Reshtikin 12 TQFT as well. It coincides with the original one. So in our theory, the TQFT contains both 12 zero and the Reshtikin 12. And they are just kind of blow up of by the 2 different colors. For 12 zero, we have A color in the background. And the skeleton of the triangulation will be blown up. And inside the skeleton is the B color. And that's the 12 vertical cavity is really similar to the tensor network. And for the Rashid-Tigan 12, we blow up the links in the 3 manifolds, and which has A color inside, B color as background. And in our theory, we have this AB color theory. So now both colors make more sense. A color corresponds to something trivial, and B color is the bulk color that gives the bulk boundary duality. And in particular, we can rate the original TQFT even with boundary condition. Like for the original 12 TQFT, we can have the boundary surface with triangulation. Now we have those kind of, that correspond to a boundary condition such that all the B color regions are just disks, they are contractible. And for Rashid-Tigan 12, we have those intersection of the boundary surface with the links. So they will be points. Now those points blow up to circles or just the disks with A color inside. So these two are really kind of fused to each other. One has boundary condition with contractible A color, the other has contractible B colors. But certainly there are surfaces with like boundary condition that neither A nor B can be contractible. So there are actually additional boundary conditions. And those are indeed very interesting. Yes, actually, at this point it's the center, but we can also construct the theory for the model tensor criteria of C directly. But we didn't show it in this talk, but that really works. So since the TQFT contains both, then we can show the two TQFT are just the same. Previously, it's proved by Turev and Varelezia that they are equivalent. But now we can embed both into this bigger TQFT, and they're just the same on the cobordism category. So it's not just equivalent, but just exactly the same in this TQFT. So that shows how do we construct the 2+1 TQFT, even with richer condition. And actually, this autofolder allows us to remove all kinds of singularities in the kind of previous TQFTs. They just blow up the singularities to smooth surfaces. Now, in a similar way, we can construct a 3+1 TQFT using the previous example, the 3 category. And then, well, we can also study the point-like particles in 4 dimensions. That's the Milgauss center. It's kind of a higher dimension, 1 dimension higher analog of the Greenfield center. But somehow it becomes less interesting because in 4-dimensional case, the category becomes symmetric. There's no non-trivial braiding in 4 dimensions. And then the braid statistic just tell us this bosons or fermions for the particle type. So it seems less interesting comparing to the braid statistic in 3 dimensions. And that's actually the very important point to study lower dimensional topology, that we have non-trivial braid statistic. However, we know 4-dimensional topology are much, much more complicated than 3-dimensional topology. So what should we learn from that? There must be some highly non-trivial topology in 4-dimensional case. So now here's a point that when we blow up the point-like particle locally to the surface, so in 1 dimension, in 2+1 case, it blows up to a closed string. Now it's a surface. And then we should look at the shape of the surface. Then for surface, we know it may have like different type according to the genus. Like not just sphere, it may be a torus. And then when we fuse them, we don't have to put them like nearby each other. We can make a non-trivial knot, like hop link. So for the higher dimensional case, they have even non-trivial fusion. The fusion is not unique, just tensor product. It's non-trivial fusion. And then we can braid like 2 particles together and fuse them as hop link and then move them away. And this will give highly non-trivial braid statistic for membranes. So indeed, the higher dimensional statistic is much, much richer than the lower dimensional case. And we should expect to study more about that in the near future. Well, thank you for your attention.
Okay, so many thanks to Professor Liu for his wonderful talk. Any question or comment?
Thanks for your talk. You mentioned that we can obtain a gapped Hamiltonian from the functional z. Can you mention briefly how to do that? Thanks.
Yeah, like for the 2-dimensional case, once we get a 2 plus 1 TKFT, then we can construct some very concrete cobordisms. And the cobordism will be action on the 2D model. And using the cobordism, we can construct certain operator that's local operator, like Plackett operator. And those operators will map the lattice. So previously we have the boundary, like on torus, we have the lattice shape. So we have AB color. And the map will just kill all the A color part. And eventually we will have a torus that's boundary is just purely B color. And the B color theory will be the original theory for in the TQFT. And that's how we implement the ground states as a space of TQFT. It's just how do we kill A color using cobordisms. And that's the Hamiltonian.
Can we reverse this process, say, from a Hamiltonian in the form like a toric code and reconstruct the functional z?
Yes.
This
yes, we can inverse that.
What if we start with a gapless Hamiltonian?
For example, for toric code, if you look at the ground state locally, the ground state are given by those sum of loops.
Yes.
And you just take that sum of loops as function. You can take configuration, you count the number of loops. That's the function z. And that function has reflecting positivity.
What will happen if we start with a gapless Hamiltonian?
Well, that will be the enriched theory. Yeah. That will have some interesting average for the gap theory.
Okay, thanks.
The n categories you get, are they strict?
Oh yes, those categories are strict. Since for a construct example, we are looking at those kind of lattice. The shape of lattice make it strict.
Any other question? Comment? Okay, so if now let's thank our speaker again. I think we'll resume in approximately 15 minutes.
你可以这个